to introduce Professor Asmaa from Western Washington University, so just up the road from us. She started there a couple years ago, and before that, she was a postdoc at the Carnegie Institute of Science with working with Peter Driscoll, who some of you might remember, who was a postdoc here about 8 years ago or so. Before that, she was at Johnson Space Center, and then she got her PhD before that at the University of Blaise Pascal in France. Asmaa is an expert in interior processes on exoplanets, and so it's a real privilege to get to hear tell us today about Mercury and its astrobiological implications. I also want to just mention that we'll be taking Asmaa out for dinner tonight, so if you're interested in joining us, please come find me after the seminar, right at the conclusion of the seminar. So with that, the floor is yours.
Thank you very much. Thank you for the invitation. Thank you all for being here. All right. So today I'm going to talk about Mercury and its internal structure, chemical composition, and astrobiological implications. So Mercury can be considered as a planet of the extreme. It is the innermost planet of the solar system. Sorry? Yeah, okay. So it's the innermost planet of the solar system, the smallest, the densest. It has the largest core and the highest variation in temperature due to the very slow rotation and lack of atmosphere to equilibrate the temperature across the surface. So the first time we visited Mercury was with the flyby Mariner 10 in the 70s. And much later, we had the first orbiter on Mercury, Messenger, from 2011 to 2015. And so most of the data from the planet that I have here comes from that late mission, Messenger. And so Messenger showed that the surface is dominated by impact craters. And we see some smooth plains showing that we had flood volcanism, as well as some local pyroclastic deposits, suggesting we had explosive volcanism as well. And the last volcanic activity dates from 3.5 billion years. Mercury also has axisymmetric magnetic field, which is really weak, much weaker than Earth, 1% as strong as Earth. And it's likely driven by a thermocompositional convection in the core. So Mercury is the only other terrestrial planet that has a magnetic field other than Earth. And Mercury is known to have this very peculiar structure. It has a very thin mantle and crust and large core. And the core has a solid inner part and a liquid outer core. Messenger also found a very low oxygen fugacity of the planet, so it is very reduced. Because that is testified by the large iron core and also low abundance of iron oxide on the surface of the planet, only 1.5% iron oxide. It also showed that the surface, silicate surface, include volatile elements like sulfur, carbon, chlorine, and potassium. And it is a heterogeneous in composition. We see different geochemical provinces on the surface. So the volcanism as well, the silicate volcanism might be a little bit complicated and suggesting complex properties of the mantle. And so here is the structure of all the terrestrial planets that we have in our solar system. And so you can see here how large the core of Mercury is. And however, even if it is the largest in our solar system, it's not the largest among planets that we know of, since we know that exoplanets, shown with these tiny dots here, can have varying density. And many of these exoplanets actually have a density as high as Mercury, so with the large core as large as Mercury. So now if we look at this, what does it tell us? That the core is large and we have a very small abundance of FeO. So if we put this together in the whole context of the solar system and focusing on the inner part of the solar system, what terrestrial planets are, so we see this increase of iron oxide for different planets when you increase the distance from the sun. So you have more and more iron oxide. And at the same time, we see a core, the size of a core that is larger and larger as you get closer to the sun. So the abundance of iron metal decreases with heliocentric distance. And so this shows that iron is present mostly in the metal form close to the sun and in oxide form away from the sun, and that is within our inner solar system. So we have more and more oxidized conditions when you increase the heliocentric distance. And the question that we can answer is whether this trend is inherited from the protoplanetary disk, or if we had later events that had an important role on this, ending up with this trend for terrestrial planets. And especially for our case with new data on Mercury, we can test some models and see if this particular composition of the planet is due to this trend that we kept from the protoplanetary disk, or if we had other events modifying the chemistry of the planet. So we can look at this trend here again in chondrites. And so chondrites are primitive meteorites that testify of the early processes of the solar system. And so this Eurythmic diagram is known to show this oxidation state of chondrites. And you see that different families of chondrites have different proportions of iron present as an oxide or metal and sulfide. With, for example, ancestite chondrites being the most reduced, with all of the iron present as a metal and sulfide phase, and almost none in iron as oxide. While for carbonaceous chondrites, you can see that carbonaceous chondrites are a lot more oxidized, and almost all of the iron is present as an oxide and has a very low abundance of iron metal. And so where are terrestrial planets in this trend here? There, you can see that we don't have a perfect match between terrestrial planets and chondrites, but their composition really still lies within this broad trend of the solar system redox. And so here we plotted asteroid Vesta as well. And as much as this trend tells you about the redox of the solar system, it also gives you information on how the iron over silicon ratio changes in the solar system. So each of these lines represents a constant iron silicon ratio. And as you go up right here, you increase abundance of iron relative to silica. So now we can plot here the composition of Mercury in this diagram. But with Mercury, it gets a little bit complicated because in reduced conditions, you end up having silicon in the core of Mercury. And so now we have a big trend. Instead of having a small region of the chemical composition of Mercury, we have much broader composition here due to the uncertainty on the composition of Mercury's core. If you have 2 weight % silicon in the core, you end up way up here above the trend of the rest of the solar system. And if you have 40 weight % silicon in the core, you have a composition closer to Earth and ancestite chondrites. And also you can see as well that there is one chondrite that has a composition very close to Mercury here, CB chondrites. It's a Bencubin chondrite. It is a carbonaceous chondrite, which makes it not very likely to have formed Mercury. And so this can be shown here. These are isotopic composition of different meteorites, stony meteorites. The carbonaceous chondrites are shown here, and other stony meteorites here, other chondrites, ancestite, ordinary chondrites, Earth, Mars, and Moon, and other stony meteorites. And so here we see two different reservoirs with stable isotopic compositions. So stable isotopes gives you information on the composition of the solar system and the different nucleosynthetic components left from former nucleosynthetic processes from former stars. And so the solar system got mixed during planetary accretion, but we didn't homogenize the whole solar system. And we still had two reservoirs, two different heterogeneities and isotopic composition in the whole solar system, with two main reservoirs, one for carbonaceous chondrites and one for the non-carbonaceous chondrites. And we see that not only for stony meteorites, but also iron meteorites. And for specifically for iron meteorites, we were able to date the separation between the two reservoirs using the hafnium tungsten geochronometer. And it has been dated to be formed at around 1 to 3 million years after the solar system formation. So in the solar system, we had some event that actually separated two reservoirs, one for the carbonaceous chondrites and one for the non-carbonaceous chondrites. And for that chondrite that I showed in the Urey query diagram, the slide before, the CB chondrites that match Mercury, you can see that it fits in here in this carbonaceous chondrites, which make it not a very likely composition for Mercury precursors. So now going back to our questions about the origin of this weird trend on oxygen fugacity here, I wanted to mention here that dynamical simulations with antibody simulations show that if you start with the solar system with planetary embryos that have different chemical compositions, and for example here, water content, you, even with different mixing processes with planetary formation, you still have a remaining zoning in the solar system. So you preserve heterogeneities in the solar system despite mixing of those different embryos. And so now we have messenger data about Mercury. So the question is, does the weird composition of Mercury comes from this trend in oxidation state and volatile element abundances, or other processes led to that? So in this talk, I'm going to focus on three main questions. The first one is, why does Mercury have a large core? The second one is, if Mercury is depleted in volatiles, and what volatiles? And finally, how this low oxygen fugacity and large core size affect the internal heating of planets. So different scenarios were proposed to explain this large core. So first, it was suggested to have been due to the evaporation of part of the mantle and crust by a hot sun. If Mercury was formed very close to the sun, you might have very large temperatures and evaporate most of the mantle. However, it predicts very high abundances of alumina, which is very refractory. It can withstand the high temperatures. And elements like sodium, potassium, and sulfur, which are volatile, would have been depleted. So since messenger measured significant abundances of these volatile elements and didn't see any alumina enrichment, this model can be ruled out. So Mercury's large core cannot be due to just evaporation by the hot sun. Another model was suggested, specifically the aerodynamic sorting, where planetesimals can be, during many collisions on planetesimals, you break down mantles and crusts a lot more easily than iron cores due to their low rigidity, but also to the fact that they're not as exposed as those silicates. So you end up forming large metal boulders and small fragments of silicates. And if you have aerodynamic sorting, you might end up with some regions that have a lot more metal than others, and that would explain why Mercury would have a large core. And another process, for example, photophoresis here, implies that close to the sun, you're away from the optical thick disk, and so you end up with starlight affecting the motion of different particles, and due to the relative differences in thermal conductivity of different particles, you can have a segregation between metal particles and silicates close to the sun and end up forming a planet that has a lot of more iron metal than silicates. And finally, a very common scenario that was proposed to explain this large core was a giant impact. So you had a proto-Mercury planet that was much larger, and with one or many impacts, you just stripped some of the mantle and ended with a planet like Mercury. So now, how do we end up having a lot more information? How do we differentiate between all of these models and find a scenario that is more likely to explain this large core? So for these two models here, they imply the enrichment of mercury in the metal that is formed at low pressure and temperature in small planetesimals, where reactions that end up having the chemical composition of the metals are reactions happening at low pressure and temperature. But for this giant impact, you would form a lot larger body, and the iron metal that you form experience a lot higher pressures and temperature during planetary differentiation. So we can look at some tracers of these conditions of pressure and temperature. And so here we're going to focus on major elements. So one major element that has a signature of a high pressure that is affected by pressure and temperature is silica. And so silicon here, we can use experiments from the lab to look at how silicon solubility in the metal here increases when you change pressure and temperature. And so these are many data from the literature here on experiments showing that silicon concentration in the iron-rich metal increases with temperature. So for example, here, these yellow dots here show that you have more silicon in the metal at high temperature. And so which means that if you form a planet a planet with a core formed at high pressure and temperature, you're more likely to have an enrichment of iron and silicon. Okay, yeah. So sorry, okay. And so if you have a large body, then you have a core that separates at high pressure and temperature, and you're likely to trap not only iron in the core, but also silicon. But if you form these metal particles at low pressure and temperature, you only have an enrichment of iron, because these particles, all of these metals form at low pressure and temperature. Okay, so we have something, a tracer of these that can help us understand why Mercury has this large core. So all we have to do is look at how much mercury, how much iron and silicon are in Mercury, if Mercury is enriched in both elements or not. So we need to calculate the bulk composition of the planet. So how much core plus mantle plus crust. And so how do we do that? So we just work with mass balance calculations. The bulk silicon, for example, equals the sum of all of the silica that's in the mantle and crust and silicon from the core, weighted by, so the concentration of elements in all of these, weighted by the mass fraction of the bulk silicate mercury, mantle and crust, and the mass fraction of the core. So do we have these? Where we have data from Messenger, which had the X-ray spectrometer and was able to collect X-ray fluorescence data, which gives us the chemistry of the surface of the planet. And with surface composition, we can reconstruct the composition of the mantle, knowing mantle properties, melting properties of the mantle, and how elements distribute between crust and mantle during the formation of Mercury. So we have surface composition, so SIBSM here, and the gravity field measurement by Messenger gives us the core fraction, the mass fraction of the core, which is about 70%. And so the mass fraction of mantle and crust, and it's just the remaining 30%. And so all we have left as an unknown here is how much silicon is in the core. So we can't access the core. We can only rely on thermodynamics and experimental data. So we run experiments in the lab at high pressure and temperature and look at how much silica distributes between the mantle, the silicate, and the core, metallic core. And so we calculate this partition coefficient, which is the distribution of this element between the two phases. And if we know the abundance of SiO2 in the mantle, and we know this ratio, we can calculate the silicon in the core. And so we can construct the whole composition of the planet with all of these data. And so this is what we did here. We looked at this reaction, which is just simply an exchange of silica between metal and silicate. It's a redox reaction. And we calculated this partition coefficient. And by looking at many data, we constructed a thermodynamic model predicting this partition coefficient as a function of pressure, temperature, oxygen fugacity, and chemical composition of the metal phase, sulfur and carbon in the phase, as well as the chemical composition of the silicate. And all this equation here just comes from thermodynamics, which shows that the equilibrium constant of a reaction is related to the activities of the products and reactants, and also equals the free Gibbs energy is related to free Gibbs energy, which can be decomposed into enthalpy, entropy change, and volume change. So all of these factors that you see here, A, B, C, D through H, are just simply constants that derive from this. Like you see here, a constant over T, a constant, and a constant times P over T. So this is just a thermodynamic model that is built from experiments. And so now with this equation here, we can predict how much silicon distributes between metal and silicates at any condition of pressure, temperature, oxygen fugacity, and chemical composition. And now if we look at the experiments here, we clearly have a trend here. So I selected here just experiments at the conditions of Mercury's core formation, 5 gigapascal. And you see that when you decrease oxygen fugacity, you have more and more silicon in the metal. But if you're oxidized, this is how much oxidized. If you're going to the right, you're more oxidized here. You have less silicon in the metal. So with Mercury, with this low oxygen fugacity, there's one more complication with Mercury, is that we have to take into account of sulfides. So sulfides can form in these weird low oxygen fugacity environments due to the immiscibility between iron sulfide and iron silicon alloy. And so as much as for some experiments, we see just one metal here with the silicate, sometimes when you have a lot of sulfur in the system, you can have two metals, two liquids, one that is iron rich, silicon rich metal, and the other one that is a sulfide, FeS. And so this this is nicely shown with this ternary diagram, where this line separates the fields between the region, the chemistry, where you have one liquid and two liquids. So we have to work with this additional complication here, but it's fine because we know we have data from experiments to understand that. And for example, here in this ternary diagram, I plotted the composition of chondrites. The chondrites plot here, they show a big range because of how we have a lot of sulfur in the system in chondrites, but that varies too. And also, as I showed previously, when you decrease oxygen fugacity, you increase silicon in the metal. So you move up in this diagram here toward the FeSi endmember. So the composition of your metal can change. Your composition changes because of oxygen fugacity, and how by decreasing oxygen fugacity, you have more Si in the metal, and so you can move in this field. So yeah, and so now with knowing all of that, we can calculate bulk composition of mercury without any sulfide layer and with the addition of a sulfide layer. And we can look at things like iron silicon ratio that I talked about earlier in this talk. And so now here, I'm going to show this bulk mercury iron silicon ratio as a function of oxygen fugacity and compare that with chondrites. So chondrites are shown with these fields here. And so how's it going to be for bulk mercury? Well, you remember here, when you decrease oxygen fugacity, you're able to include more silicon in the metal. And so the bulk planet will be enriched not only in iron, but also silicon. So when you decrease oxygen fugacity, you end up having a smaller iron silicon ratio because of this additional silicon in the metal trapped in the metal. And so you're able to decrease this iron silicon ratio by incorporating that element in the core. And one can look at scenarios where we have a sulfide. And so sulfides actually, they replace some of the mantle in this model. And so if you replace some of the mantle, you increase iron and you decrease silica because you're taking some of the silicon that was originally in the silicate mantle and crust. So you have slightly higher ratio for these models. Now, Mercury has this really large core, so we do know that the chemistry is different than other planets, and this can be just seen with oxygen abundance. As much as we can change the chemistry of the core, you can't have oxygen in the core, so Mercury is depleted in oxygen compared to all chondrites and other planets. So just for these first calculations here, Mercury could have a chondritic iron silicon ratio, but oxygen remains significantly depleted than chondrites. So now we want to know if we have, remember, if we have an enrichment of iron and silicon in order to know if it's an impact that generated this large core or not. So I'm going to look at other ratios that have iron and silicon. And so see here we calculated iron magnesium, and you see that it is always higher than chondrites. So we do have an enrichment of iron for Mercury. And silicon here, silicon is also enriched for a range of oxygen fugacity. So see here, if oxygen fugacity is lower than IW minus 3.5, we enrich the planet in silica relative to chondrites. But if it's more oxidized, we have as much silicon than other chondrites for other planets. So we do observe an enrichment in iron and silicon in Mercury if oxygen fugacity is low enough. So can we use other geochemical tracers? So, so see here we have maps of Mercury's surface composition. And so we can look at other geochemical tracers like chromium, for example. So we did that recently with a collaborator, Larry Nicker. And we were able to get chromium concentration, and we can do the same thing, just try to look at how much chromium is in the Mercury by looking at the partition coefficient between metal and silicate and sulfide silicate. So again, how much chromium can be trapped in the core versus sulfides of planets. And see here, we observe that chromium can have more affinity with metals and sulfides at low oxygen fugacity, high temperatures, and high sulfur concentration. So it is important to take into account of how much chrome is in the core and sulfide of the planet to address that bulk composition. And so we did the same calculations here, same thermodynamic models, and we calculated this bulk chromium, aluminum, and you see that it is, we can find a ratio that is similar to chondrites for a certain range of oxygen fugacity. As long as the planet is not too reduced, we do have models that match chondrites. And so, so now to summarize on these chemical composition of Mercury. So if Mercury is moderately reduced, not too reduced, we have an enrichment in iron, but not silicon. Silicon would be chondritic, and that would favor what we can call orderly models, models like photophoresis, aerodynamic sorting, magnetic sorting. But if you have a planet that is very reduced, then we would have iron and silicon enrichment, and that would suggest a core from a large, the presence of a large core due to mantle stripping by impacts. Okay, so now what do we do with all this? Like, do we have any clue about that? So as much as there's this big uncertainty on oxygen fugacity for Mercury, a paper actually was able to estimate oxygen fugacity of the surface by looking at sulfur abundance on the surface of the planet. So the data from experiments here show that when you decrease oxygen fugacity, you increase the solubility of sulfur in the magma. So you can have a lot of sulfur in the magma, as much as 10, 12, 16% sulfur can replace oxygen in the magma itself by forming S2- complexes. And so this is why Mercury has really large abundances of sulfur on the surface. And by using this information, we can estimate how oxygen fugacity is in Mercury. And we see that the range is really low. Oxygen fugacity on Mercury can be as low as either V-6, 6.5, so super reduced planet. And so now with this data here, we can just give a little bit more likelihood to the scenario of large impact here, because it implied that the planet was very reduced. If we just showed that if the planet was super reduced, the formation of this large core was due to an impact and not orderly processes. So yeah, so this just showed that we have the large core might likely be due to this large impacts. Okay, so now I'm going to talk about the volatile abundances of Mercury. And so, volatile elements can be more or less volatile. There are elements that are very volatile, like hydrogen, carbon, nitrogen, and others that are moderately volatile, like potassium, sodium, and sulfur. And some elements are not volatile at all. They're refractory, like alumina, titanium, uranium, and thorium. So as much as we know that the solar system, the outer part is very rich in the highly volatiles with the gaseous planets and icy planets, then one question that we can address here is whether we have another gradient in volatiles within the inner part of the solar system, knowing now the composition of Mercury. So for example, is Mars a little bit more enriched in these moderately volatile elements than Mercury and other planets inside? And so that's what we try to address here by looking at potassium, uranium, and potassium thorium ratios. Because these two elements behave the same way during mantle cross-differentiation. So we can, whatever ratios we measure on the surface can be usually extrapolated to the whole planet because they don't fractionate. Potassium and thorium do not fractionate during magma differentiation. The ratio stays constant. So what you measure on the surface can be considered as the bulk planet composition. And so before MESSENGER, what we found was that Mars had a lot more, a larger abundance of potassium than other terrestrial planets, suggesting that maybe Mars was more enriched in volatiles. But we were also expecting that Mercury was depleted in potassium here. However, this was the data from that MESSENGER measured. We had a higher potassium than other terrestrial planets like Venus and Earth, and something that is similar to Mars. And so that was very, I would say, disturbing. And all of what we understood from that information had to be updated. So now the question is, Mercury is very reduced. So can we still consider that first hypothesis that potassium, uranium, and thorium do not fractionate during core formation? Because we do have sulfides that we never see in other terrestrial planets, and the planet is very reduced. So the chemical reactions might be different. And so we run some experiments to look at how these three elements partition between these different phases, metal, silicate, and sulfide. And what we found is that we have very negligible potassium, uranium, and thorium in the metals. So if we only have a core, that wouldn't change anything. But if we have sulfides, then things would be different, because uranium, thorium, and potassium do like to be in sulfides in these weird oxygen-depleted environments. And so we've been doing some playing with thermodynamics again and looking at these reaction exchanges of these elements between silicates and sulfides. And we see that when you decrease oxygen fugacity, you have more and more of these elements in the sulfide phase. But here, we don't have the same behavior for the three elements. You see the slopes here are the same for uranium and thorium, but for potassium, the slope is slightly less steep. And so you have less of potassium ending up in the sulfide phase when you decrease oxygen fugacity, less than these two elements. So this shows that we can have fractionation of these elements during planetary differentiation, and it is important for Mercury. So we have to recalculate this bulk potassium, uranium, and potassium thorium ratio So this is again with heliocentric distance, as much as we saw this trend for Earth, Venus, and Mars. So where is Mercury? Is it really here? Is it the surface values? So if we have only a core, mantle, and crust, yes, nothing would change. But if we do have sulfides, Mercury was reduced, we would end up with ratios that are much lower than we see on the surface. So that would be important to take into account. And in this case, if we have sulfides, then Mars would still be more enriched in volatiles than the 3 other terrestrial planets. And bulk ratios here would be similar to Venus and Earth. And so if Mercury is reduced and contains iron sulfide, it would be as depleted as Earth and Venus in potassium, and Mars would remain the most enriched terrestrial planet in moderately volatile elements. Now, I say a lot of if, right? And so because we have a lot of unknowns, oxygen fugacity, we don't know exactly where is oxygen fugacity. We don't know if we have sulfides on Mercury, so there's still a lot of work to understand that. And Bepi-Colombo, a mission that is on the way to Mercury, and it's gonna start orbiting the planet in 2025, and we're gonna have more results to address all these questions. So finally, the one last part here is how does low oxygen fugacity and core size affect thermal budgeting and internal heating of exoplanets? So I'm going to talk first about radiogenic heating for Mercury and the core state of super Mercury, so exoplanets that have a structure like Mercury. So yeah, when you have a growing planet, you have many internal sources, accretion heating, radiogenic heating, differentiation from segregating elements, and so you release some gravitational energy. You have latent heat from core solidification and possibly also tidal heating. So I'm going to here focus on radiogenic heating for Mercury and see how the presence of the sulfide layer influences heat production for the planet. And so see here, because this sulfide would replace some of the mantle, even if we have some of these elements, radioactive elements in the sulfide, we have less of those than if everything was just mantle and crust. So as much as we are able to have potassium, uranium, and thorium in the sulfides, those abundances are not as high as those found in mantles and crusts. So that by replacing the mantle with sulfides, you have slightly lower heat production from radioactive decay. So if part of Mercury was FeS sulfide, you would have less heat production. But for other planets where for example, if you form sulfides and they end up being trapped in the core, you can increase abundance of heat, radiogenic heat, if you're able to trap these phases in the cores. So that would be something that it would be important to take into account in future studies on the internal heat of planets. Okay, and so what about rocky exoplanets? Exoplanets that have a large core like Mercury. So we know that several exoplanets are found to have large cores. Most of them are larger than Earth, but some of them are as small as Earth. For example, K229b. And so here we updated internal structure of large rocky planets, super Earth, and their internal heat budget by just considering hydrostatic equilibrium, by resolving differential equations for mass, gravity, pressure, density distribution in super Earth, and by using new data on equations of state of planetary materials and their melting temperatures. So this internal structure, we resolve these differential equations numerically by calculating the total masses and radii of exoplanets and fitting those with data from exoplanets. So this is the plot I showed earlier. So what we do is by resolving all those equations, we can look at what mass would be, what mass and radius couple would match different structure of the planet. For example, a planet made of pure iron would fall on this line here, and a planet made of just pure silicates would fall on this line. And here you have different core mass fractions. So Mercury core mass fraction, Earth, Mars. And so, yeah, and so by fitting here, we're able to tell whether these planets have a large core or not, and model the whole thermal structure of the planet. We also used data from melting at shock and compression experiments. Oops. With my collaborators, Wei Fei and Peter Driscoll, who's a postdoc here. We actually got data from shock compression to get the melting curve of MgSiO3. And shown here in red, up to terapascal, so up to 1,000 gigapascal. And so we use this data with the melting curve of iron as well to look at the temperature distribution in planets, as well as pressure and density, and compare those with melting curves of silicates and iron. And so the question that we try to answer here was, how would be So the temperature, so this temperature at the core mantle boundary for which we have the solid and liquid cores coexisting becomes larger with the core mass fraction. So if we have many exoplanets with temperatures randomly distributed in these temperature ranges, there is more likely to have exoplanets, super Earths, that have this growing solid core if the core is large. But if the core is very small, like Mars, for example, there is just a small range of temperature where you can have both solid and liquid core. And so this means that when you have a large core, you are more likely to have a growing solid core. And something interesting that we found too is that this range of core temperature at the top of the core temperature is higher than the melting curve of silicates, meaning that the bottom of the mantle would be more partially melted. You might have melting there and have a basal magma ocean left over. Yeah, and so this was our conclusion for this here, is that super Mercuries are more likely to have a core in the solidification stage, making more likely to have a geodynamo driven by core compositional convection. Also, a growing inner core implies a partially liquid lowermost mantle, which might also affect geodynamics and have important implications for the geologic evolution of exoplanets. And so these are my conclusions. So Mercury is very reduced for an oxygen-depleted environment. It is likely for the large core might likely due to a giant impact stripping part of the mantle. We talked about volatiles here, that potassium, uranium, potassium thorium ratios show if you incorporate core and sulfide compositions, it is still possible that Mars is more enriched in volatiles, and we might have preserved some volatile distribution, gradients within the inner part of the solar system. And finally, yeah, for super Mercuries, actually they might have more likelihood of develop a geodynamo due to this big range of temperature for which they have a solid growing core. Okay, thank you.
Very much, Asmaa. So it's time for questions.
Yes.
So, how much carbon can you put in the core? And also, looking far into the future, when the core goes almost completely solid, how concentrated can silicon and carbon get in the last molten part of it? So really, that's percent. I guess it can, but
yeah, so you have some solid phases. You have iron silicon alloys that are solid that can form, and carbon as well. But you do end up concentrating these light elements in the liquid core, and at some point, I think in time, you might end up with carbon solubilizing in the mantle and forming SiC, for example, silicon carbides. Especially in these reduced conditions, you might form silicon carbides.
there's some people have suggested that most of the Earth's carbon is in the form.
Yeah. Mm-hmm.
So it's not a volatile in that sense.
Yeah, if you solidify it from the nebula, I mean, if you condense carbides in the nebula, but so still we don't have a lot of carbon. So you know, as much as the core composition, Earth core composition, it's very, very controversial. Each paper has a favorite element. Like one paper has a lot of carbon, another one sulfur, one oxygen. Yeah. But the problem is that you have to condense it at first from the nebula in order to have that and being trapped in the core permanently in the planet. And meteorites you don't have carbon-rich iron meteorites. We don't see any carbon-rich iron meteorites or those are very, carbon is not that abundant in primitive meteorites, yeah. Mm-hmm.
Well, that's, I have a couple of related questions.
Mm-hmm.
Mostly the what you show in the surface results. Are we confident that there is representation of the molten mountain
Of the mantle of Mercury?
Yeah.
Yeah, so it is very strange for Mercury having such a large oxygen fugacity range on the planet. Oh, we see something. So here, for example, see we have a very large range of oxygen fugacity, kind of like for 2.5 orders of magnitude, log, yeah, orders of magnitudes for oxygen fugacity. And so for something like Mercury, yeah, you might have a very homogeneous oxygen fugacity in the surface and the mantle, and that might be very important for Mercury. For example, if you form Si metal in the mantle of Mercury, then the silicate matching properties are different. You have more olivine than pyroxene and sulfur also. So Mercury is very complicated because of that.
Thinking about geochemistry, it sounds like much the same. The very reduced state of Mercury across the mountain is like a consequence of the large core size and the consequence of the low oxygen environment formation. So we wouldn't, is it true that we wouldn't necessarily expect the Mercury to have really reduced mountains and to have new mountains or not a huge even the combination of a lot of impact on the environment.
Yeah. Yeah, very good question. Very good question, but very hard to understand because I mean, this will work with on Mercury, and I can be like, oh yeah, Mercury's large core is due to impacts within the mantle. So all super Mercuries have the same process. Like there's so many different things out there, and so yeah, but of course, your main point was right. Like a planet with a large core is not necessarily more reduced. You can have something that's oxidized with a very large core. You know, if you just strip the mantle of Mars, you would still have a large core and stay oxidized. So yeah, these are just with just data. You have to do work on these things case by case, I think. But is it a coincidence that the only planet that has a large core is also more oxygen depleted? I don't think so. So it might be a combination of both, like as much as all these models like photophoresis does not, the model that doesn't reach the size of Mercury's core, it makes like a core that is still smaller than that. Every single model doesn't reconciling the large core, so it might be a combination of processes even from Mercury. Yeah. Yes. Any other question? Yes.
I have a questions on the planet formation side. Like it seems like your data is suggesting that the Mercury is from like stripping the mantles. I am curious like how likely that happens in like for example planet formation models. And maybe related questions like how frequent do we see something like Mercury in the exoplanet observations?
Yeah, so so for the first question, so there was a paper by Bonsor that showed you have 10 to the 5th impacts on average for a planet as big as Earth. So you do have a lot of impacts. I don't know if that answered your question. And there are some numerical models that just show that impacts stripping part of the mantle. And I don't know if that answers your first question. And the second one was on What is it again?
Well, maybe exoplanets, exoplanet.
Okay,
How often do we observe something that looks like?
yeah, not a lot. But still, we don't have a lot of super Earth and exoplanet, rocky exoplanets data. I mean, the fraction of super Mercuries over all of the super Earths is still very small. Yeah.
All right, were there any questions online?
No.
All right, well, we've reached at the top of the hour, so why don't we thank Asmaa again for a fantastic talk. And if you're interested in dinner, don't forget to come down and let me know, or you can let me know where you move. Great,
Okay.
yeah, that was
Nice.
awesome.
Okay.
Yeah. Never been too excited about Mercury, but it's really fascinating to see those connections I had not seen before.
Oh, yeah.
That connects to the
I'm
formation
excited about
models and-
Mercury.
Yeah, really. Yeah, it's
Oh,
fascinating.
thank you.
I didn't ask my question because we ran out of time, but with the last result you had on the magnetic field, it really was more about the partially melted